Welcome to Summarize Science. Ever wonder what's stopping us from making computers even smaller and faster? A big hurdle is the stability of the tiny switches or transistors that are the building blocks of every chip. Today, we're looking at a paper that tackles a major stability problem in next-generation transistors made from super-thin, 2D materials. These advanced, tiny switches often have a weird and unwanted memory effect called hysteresis. Imagine a light switch that acts differently depending on how recently you last flipped it. That's hysteresis. This inconsistency is a huge problem for reliable electronics. For years, scientists have reported this effect, but often with vague descriptions like negligible or small, without a clear definition. This paper highlights a huge issue. Everyone measures this memory effect differently. As you can see in this chart, depending on the test frequency, one device can appear more stable than another, and then the trend can completely reverse at a different frequency. This makes it nearly impossible to compare results between different labs and different devices. It's like trying to compare race cars when nobody agrees on what a mile or an hour is. To fix this, the researchers first comprehensively analyzed the main culprits behind hysteresis. They identified three dominant mechanisms: charge getting trapped in defects, mobile charged particles wandering around where they shouldn't be, and a material property called ferroelectricity. Crucially, they show that these different causes create unique, identifiable signatures. For example, charge trapping near the main channel causes what's called a clockwise hysteresis. In contrast, the other sources, like mobile charges or defects near the gate electrode, cause a counterclockwise hysteresis. This allows scientists to play detective and figure out exactly why their transistor is unstable. This brings us to the paper's main solution, a standardized measurement scheme. The core idea is to create a universal ruler for measuring hysteresis that everyone can use. They propose a specific way to test the transistors, carefully adjusting the test voltages based on a key property called the equivalent oxide thickness, or EOT. By using this standardized method, the results can be properly normalized. Here you can see the raw measurements, which are all over the place. But after normalization, the curves for different devices line up perfectly. This allows a fair comparison between a thick prototype from one lab and a thin one from another. Amazingly, it even lets them predict the stability of future, ultra-thin transistors that haven't even been built yet. So, let's recap the important points. This work provides a way to finally understand the different physical causes behind transistor instability. More importantly, it establishes a standardized protocol so that researchers around the world can finally compare their results on a level playing field. This turns hysteresis from a poorly defined problem into a reliable diagnostic tool. This systematic approach is a potential game-changer for developing the next wave of electronics. It enables the rapid screening and benchmarking of new materials, paving the way for the stable and reliable 2D material transistors needed for the future of computing. Thanks for watching Summarize Science.